Okay, so our next learning plan is here on module number 6. It's going to be on belt and chain drives, and it's going to be chapter 11 in our textbook. As we go into the learning plan here, chapter 11 PowerPoint presentation is here. We're going to be referencing that as we go through. But if you wanted to, we are going to be going back and forth to the book. This starts on page 302 in our textbook, and then we'll be covering the section that you're responsible for that will pertain to the homework assignment that you're going to have. So we'll kind of talk about the homework when we get done with everything. So I'm going to start by opening up our PowerPoint presentation, zooming out just a little bit here. And then as it says here, chapter 11. So the objectives that we're going to have here for this particular chapter are to look at belt and chain drives and identify their advantages, where their applications would be most suited, looking at different types of belt and chain drives themselves, looking at the kinematic relationships for each one of those, and then also making sure that we can identify using standard sizes what your whether it's pulleys for a belt drive, or if it's going to be sprockets for a chain drive, what the two sprockets or shivs would be for each, and then what the belt or the chain length would be as well. Okay, now I want to remind you that we are in kinematics. So when we're in kinematics, we're not worried so much about, as you know, forces. We're mostly worried about what is the motion that we're transmitting and creating and needed, and also what is the spatial, relationships that we need to maintain. So belt and chain drives are going to be used to transfer power between rotating shafts. Belt and chain drives are going to offer flexibility on center line that gear drives don't. Gear drives have to be up against each other, okay? Belt and chain drives can be further apart, okay? So they offer that flexibility of kind of that distance, that center distance being able to be variable, okay? Sometimes gears can become impractical when those distances on those shafts have to be kind of large. So a bicycle chain is going to be a classic example that I'm sure we've all experienced, where we have the drive is going to be by our pedals, and then the output is going to be on the rear wheel. And that chain mechanism is going to transfer the forces and the motion. And in kinematics here, we're most concerned about the motion from that rotating pedal assembly to that rear wheel. So the velocity ratio of that chain can also be altered by changing the gears. And then it just kind of shifts that chain or pushes it back and forth along the gang, if you would, of sprockets that we would have on either the front and or the back, right? Changing those velocity ratios is going to be much more complex on a gear drive than it would be on a chain drive. So we end up using something more simplistic for a bicycle as opposed to like a transmission in a vehicle, okay? Now, flexible connectors, belt and chain drives are considered flexible connectors because they connect input and output motion for things that, have variable distances. Belt and chain drives, their kinematics are exactly the same. So that's why we kind of cluster them together. So we're going to look first specifically at belt drives. So starting on page 302, section 11.2, this is where we start with belts. So first and foremost, their function is to transmit rotational motion and torque from one shaft to another in a smooth, quiet, and inexpensive way. All right. So the advantages here of belt drives, number one, they're pretty low cost. They're very readily available and used on a number of different applications. Can we list some? Say that again. 3D printers, absolutely. Yep, there's belts on there. Where else? Serpentine belts on cars. Yep, what else? Belts. Belts. Motorcycles have belt drives. You can do belt drives on those.
There's actually also bicycles.
Are there bicycles? Okay, all right. Any others that you can think of? Anybody snowmobilers? There's belt drives on those. A lot of different, what else? Oh, okay. Are there? Oh, Yeah, there are tanks. What was that?
Grocery, belts.
Oh, the belt on the conveyor in the grocery. Absolutely. Yes, 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 yes. So they're used in a lot of different applications. Now, again, flexible center distance as we've talked about, but probably their biggest advantage is that they're going to be quiet and a little bit more smooth. Okay. When we have gears, they're going to be metal on metal. So we can usually hear that, you know, the lubrication is going to minimize some of that noise, and then maybe if you have a housing around it, but there can be noise associated with that because it's metal on metal. Same thing with chain drives. We'll be looking at chain drives a little bit later, but knowing what you know about chain drives, again, metal on metal, it has to go up between the teeth on the sprocket, and you end up having some noise there. Where belt drives, they're quiet. Those belts are fabric and rubber, and you don't get that noise. So that's usually one of the biggest advantages and one of the reasons that they're used in certain applications like 3D printers, for instance. You don't want, you know, belt drives or chains, you know, kind of clickety clacketing around. You want to keep it a little bit more quiet. Same thing with automobiles. Keep them a little bit more quiet under the hood. Sometimes you can't even hear engines running anymore, right? Unless you're right up against them sometimes. So they also don't require any lubrication. Chain drives do, okay? And so do gears, as we know. They are easy to assemble and to install. They don't require much maintenance. Usually when you start seeing it cracking, or if it starts to slip because it's lengthened a little bit over time, it's time to just change it out, and it's kind of like you're ready to go again. And then they're also good at absorbing shock loading because they have that give because of the fabric and rubbery material that they're made out of. So if we look at page 303, that's where we're going to start seeing some of the different types of belts, but the materials that they can be made out of are a combination or, you know, one or the other of some of these. So first of all, there's leather, fabric, rubberized fabric, there's cord, there's reinforced plastic. So a lot of different types of materials that can be used and brought together as like composites, if you would. Oh, CVTs. What's a CVT? Oh, a continuously variable transmission. What was that? Oh, yeah, that's right. Okay, thank you, Evan. Good, 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 good. Now, types of belts, we're going to look on page 303. I'm going to go underneath, and we're going to notice that these are the most common types of belt drives that are out there. There are going to be other configurations, and different companies are going to come up with their special little spin on things, but these are going to be kind of the run-of-the-mill basic ones that are going to be found. So first of all, there's a flat belt. So that's going to look very similar to, you know, what we see, for instance, on a conveyor, on a grocery conveyor. And then here we have a V-belt, just a single V-belt, probably the most popular kind. Now, this form of this V on either side is going to fit down in, I'm going to go down here. This is the cross section of a shiv. Okay. Now, I guess I'm going to ask, I'm going to presume that many of you have a little bit of experience, or at least understanding of what a V-belt drive is with the pulley and the V-belt. Everybody kind of have that understanding-ish? Okay. All right. I'm seeing nods, and I'm hoping online, very same thing. And so the form of the V is going to fit down in the pulley itself, which is going to accept the belt. So it's important that the belt match up with the pulley, okay? And we're going to find that there are a couple different types. There's a 3V, a 5V, and an 8V. And that's all that's going to do is it's going to give us the size of each one, okay? Jesse, I'm going to ask you a really big favor. Just be careful with your soda because there's not a cap on it. Yeah, so now it's like pressure's on. At least for me, it would be. Yeah, they ask, actually, there's a sign, it says no food or drink. I'm not a big deal about that. I understand because I like to eat and drink as well. But then I just ask that you have a cap on it. That's all. In case it just spill over. But just be careful. That's all. That's all. All right. So anyway, so these are the different sizes. So you're going to notice that 3V is going to be the smaller, less heavy duty, and then the 8V is going to be the largest one. And then we'll talk about this chart in just a little bit. But if you have a 3V belt, it has to line up with a 3V pulley, okay? And the same for a 5V and or an 8V. Now this is a single V belt, and you'll notice that it has different layers here. And this is where you're gonna have like some rubber area, you're gonna have some fabric area, and then reinforced with usually some steel cord in there so that it has some really good durability. The next ones that we have here are multi-V belts, and all that this offers is additional friction for our V belt to be able to perform. So as we look down here, when this snugs down into the V, it actually creates, friction to stay in place. Now, V belts are going to get to a point where if they're overloaded or jammed, they're going to start slipping. And that's by design, okay? There's going to be a point where they're going to. And in this case, all this means is we're able to have more friction so we can transmit higher loads, more horsepower, more torque through that, okay? The next one that we see here is the cogged belt. Now, the cogged belt is going to be a larger size, but these little notches that are in here are not to catch teeth on a sprocket, or I'm sorry, on a sheave or a pulley, but they're actually there to make the corners easier to go around smaller radiuses, okay? But a timing belt, on the other hand, has actual teeth that are going to fit down into what we call a timing pulley. And then that's going to be kind of the best of both worlds, like kind of like a gear and kind of like a belt, but it has the flexibility of the center distance, okay? So these are actual teeth that would fit down into a timing pulley. We're going to focus in here on the V-belt drives, again, because they're the most popular, but the kinematics and sizing would be the same for the other ones as well. Okay. So materials, we talked about those. Now, sheaves or pulleys, those are really interchangeable terms. So sometimes you'll hear me say sheave and sometimes you hear me say pulley, same thing. So they're going to be the wheels that are connected to the shafts and they're going to carry the belt, okay? If we take a peek at page 304 in our book, we're going to see an actual drive down at the bottom here. And I think it gives us just a better picture of how these are arranged. So over on the left-hand side here, this is the side view of the pulley, and this is going to be our V-belt over the top. So if we would look in this direction, we would then see the actual V cross-section of this pulley right here, okay? You'll notice that we have a smaller pulley and we have a larger pulley. The smaller pulley is most often going to do that same thing that a pinion does in a gear and a pinion combination. And the pinion is going to be the input, and the smaller of the two, it's gonna rotate at a higher velocity. And then the larger one is going to be the driven. So many times we refer to this as the driver, as the small one, and the driven as the larger one, okay? Now, as we go around, these are going to have rotational speed. The W1 in this case on the left-hand side for the smaller sheave is going to be the one that's going to go at a larger RPM. And then this one is going to be going at a slower RPM. You'll notice that they have a slack side and a tight side. And that is simply because as it pulls around, that belt is going to be tighter on the bottom than it is on the top. We'll talk about when we get to the equations and how the center distance kind of relates, but the center distance is going to be this distance between here. But because of the sagging that can occur on that slack side, there is a range for that center distance optimally that we want to operate within, okay? The other thing that we're going to be interested in on this belt drive is the amount of wrap that we get, okay? So the amount of wrap we get is directly proportional to the amount of friction that we have as it goes around. So the more wrap we have, the better, if you would. The less wrap that we have, not so good. So there's going to be, I think, I want to say the number is 120 degrees or greater. We want to have wrap of like contact on the pulleys. So we always check that when we, create our designs. Oops, I opened up Creo. Shoots. That's so similar to my other one. Do you do that too? Yeah, I'm going to push this over here. All right. Sheaves are going to be classified by their pitch diameter. So if we go back and we look at page 303 again, and we go back to this chart I briefly looked at, you'll notice that we have these columns of the different sizes of V belts. Okay, so again, the 3V, 5V, and 8V, and the smaller the number, the smaller the physical size of that V belt. Now, in here, we're going to look at the pitch diameters. Now, the pitch diameter is going to be identified, and we'll see it here on this sheave in figure 11.2. It's kind of like the middle point on that V shape of our pulley. Okay, and so when manufacturers create their pulleys or their sheaves, they are going to be standard sizes based on the size of the belt that we have here. So you're going to notice that if you choose a 3V belt, that means that the pulleys with the pitch diameter, these are the sizes that are available to us, nothing in between. So you've got to work with what the manufacturer actually offers. Okay, so that's for 3Vs, 5Vs, and also 8Vs. Okay, so when we do our problems a little bit later on, we'll be referring back to this chart because we're going to be picking off of the standard list. Okay. Okay. Commercially available sheaves. Yep, then that's what we just looked at. So as we look at V belts, we're going to look at, example or figure 11.4. So underneath and on the next page here, on page 304, we're going to find this chart at the top. This is how we are going to be picking what is the appropriate size for us to use for our belt drive. And that's going to be based on what we call the design horsepower and the RPM of the faster sheave. So it's going to be the smaller sheave of the pair. So you're going to find your RPM here. So it can be going, 800 RPMs, for instance, and we have a 10 horsepower that we're pushing through. So if we pull those together, it's going to land right about here. And that means that it would be appropriate to use a 3V belt. Okay. And then you would do the same thing for any other applications that you have. All right. So that's how you kind of get in the ballpark. Now, I always like to say this is a good place to start. All right. There might be other considerations why you would use maybe a larger or a smaller belt. In some cases, if you're close to the edge and you have a good stock of, and you use maybe that same size belt in other places on a machine, for instance, then maybe you would consider that. Okay. So, so this is just to really kind of get us in the ballpark and, a place to start. Always best to consult with your actual manufacturer's catalog information, though. This is for kind of, blanketing over the industry, if you would. There are specific manufacturers out there. And when we're in machine design next semester, we'll be pulling out some catalogs and actually going to their resources and going through the process of sizing a V-belt drive. Okay. And that's something you're going to typically do out in industry. You're going to be, if you don't want to make everything. There's a lot of manufacturers out there making standard parts. V-belts are one of them. Okay. So you're going to incorporate their parts into your design, and you have to learn to go through their catalog and size it according to their specifications. Because if something doesn't work right, or if it starts to fail prematurely, then you're going to want to go back to them and be like, hey, it was supposed to do this and it's not. And the first thing they're going to ask you is, okay, how did you size it? And you're going to have to kind of prove, okay, we went through your process. Or if you're like, well, we kind of figured, then you're back on the hook. Okay. So, so using manufacturer's data is really important. So we'll continue to reinforce that. For here, we're just kind of starting out. We'll use the catalog page here. So belt drive geometry. So if we look at figure 11.5, which we have looked at already, this is a sketch, if you would, of the belt drive geometry. So as we had pointed out, the smaller sheave here is going to be called the driver. Okay. And the larger sheave is going to be called the driven sheave. Okay. And then they're going to be connected. The belt is going to be going over the top of them. Now, something that we have to consider when we design, and we will do this in machine elements, not so much in kinematics here, we're just starting the design process, is we're going to have our sheave be able to move in and out on the theoretical center line. So it's going to have to move in when we want to install the belt over the top, because that groove, or because the belt has to go down into the groove. And then once it's in place, we can pull it back to the center line to tighten it up. Then over time, it's naturally going to stretch out. So it has to have what we call a take up on it. Many of you have probably heard about, a belt take up. So you have to design that into it as well, so that over time, as it stretches, we don't want this to start sagging, okay, or coming off again because it's not tight enough. So there is a certain amount of take up that is expected. And again, the manufacturer will be the resource for what's appropriate for the belt that you choose, okay? Now, as we look, the distance between each one of these pulleys is going to be called our center distance. And that's the advantage of the belt drive and the chain drive as well, is that we don't have to have these elements on top of each other or next to each other so that they can interact like we do with a gear drive. Okay, these can be further apart and they can be variable. Okay, so the center distance is going to be something that we're going to be interested in. Now, there are limits on that center distance. As I had said earlier, we want our center distance to be between the number of and the size of the diameter of the second pulley, and we want it less than 3 times the driver pulley diameter plus the driven diameter. So down here, when we look, this D2 is the pitch diameter of the driven, and the D1 is going to be the pitch diameter of the driver. Okay, so once we know what those values are when we pick them, then all we want to do is we want to figure out, okay, what's the range that the center distance needs to be in. In the problems that you do for this assignment, the book isn't going to give you a number, but you most often will know a number, right? You're going to design it for an application that's like sitting in front of you. So you're going to know, is my center distance 10 inches? Is my center distance 25 inches? I don't know. So this is going to be a number that you're going to, if you would, pick out of the air, but make sure that you're between, the two numbers that create this range, depending on what you pick for your pitch diameters of your driver and your driven. Then the next thing that we're going to be interested in knowing is, how long of a belt are we going to be, specifying? Now, belts, again, are going to be something that is going to be standardized. If you ever go into like a Napa Auto Parts, there's always like the belts all hanging up on in the back of the desk, because everybody's, looking for belts. Actually, I don't know, do you guys go to Napa at all? Does anybody do that, to the auto parts store? We used to go, I grew up on a farm, and so we'd always go for belts for this thing or that thing. And we'd always walk into Napa and they were always hanging there, and they're standard numbers. And as we go to table 11.2, these are continuous belts. So they're actually spliced together. So when they're in that form, they come as a continuous belt. That's why we have to push the pulley in to get the belt over the top, and then push it back to tighten it up, because it's a continuous belt. All right. So the size of those continuous belts are going to be standardized based on the size of the belt that we're going to be calling out. So for 3V belts, these are the standard sizes of continuous belts that we have available in that size. Here's the one for the 5, or here's the list for the 5V, and then here's the list for the 8Vs. So when we're specifying our length of our belt, the length of the belt is going to be the entire length, like the circumference, if you would, going all the way around. Okay. All right. And to calculate that, we have a nice equation. Okay. So once we pick what our center distance is, we are going to then calculate what the length of the belt will be. Now, when we do this initial calculation, that belt is you're going to get like a weird number. And then what you need to do is you need to go over here and say, okay, what's my number that's closest? And then you're going to reconfigure it, and you're going to then calculate the center distance. Okay. So the actual center distance based on a belt that you can actually get commercially available. So it's kind of going to be a design iteration going back and forth. And we'll do some examples so that you can see that process. And then here's the center distance equation. This B, this is just like an intermediate step in the actual process. So you calculate B first based on whatever length you ended up picking from your standardized list. and you find out what B is based on also the pitch diameters of your shivs that you picked from the other standardized lists that are commercially available. And once you get B, you're then going to plug it into this equation with the diameters, the pitch diameters of each one of the pulleys. And then you're going to find out what the actual center distance is. Okay. So we estimate it up here. And then once we pick an actual belt, we're going to plug that back in down here and then calculate the actual center distance. Okay. The last equations that we have here are the angle of contact. And we already talked about that. And that's how much wrap we get on our belt with a minimum of 120 degrees. Okay. So you can imagine the closer that these get together, you know, depending, it's going to change that angle of wrap or the further apart that we are. So we always want to test that to make sure that we're 120 or greater.
Are we going to be adding any of these to our equation book?
You could, I guess maybe we'll do that. We'll do that when we start an example. Okay. We'll kind of organize them and kind of get them in place. That's a good idea. I don't remember if I did or not. There aren't as many in this one as we've had in the last ones. So it's more reading them off the charts. And then it's like maybe 4 equations. So, but we can, it's a good idea to bring those all together. So we talked about belt length, we talked about center distance, and then we talked about the angles of contact. So belt drive kinematics. So velocity ratio. So we're going to go up to page 305 and we're going to look at equation 11.7. As we look up here, this should kind of look familiar to us. Actually, I'm going to move this down a little bit. Okay. Here are our equations for velocity ratio. We did this in our gear design, okay? And you'll notice that it's set up exactly the same. So velocity ratio VR is going to be equal to, now the ones, okay, are going to be the driver, okay? The driver. And that's going to be the faster moving pulley or the pinion like we had on our gears, okay? The twos are going to be driven, okay? And I'm going to go capital N there. Driven. So driver is going to be the faster moving one like the pinion. Driven is going to be the slower moving one like the gear.
Is that specifically for our homework?
Just in general, just the ones. Remember the last time when we did gears, ones were the pinions and twos were the gears because the pinions were the smaller in the pair.
Right.
Okay.
Well, the only reason I ask is because like not motor world that definitely where a bigger gear drives or bigger.
Oh yeah, it can always go. Yeah. You're right. But in this case, for the ones that we're going to be using for the applications, yes, are typically going to be where we want to reduce the speed and increase the torque.
Yeah.
Right. Yeah. Yes, there are drives that can go in the opposite direction, but they're quite honestly, that's probably more industry specific as well as it's just not as common. It's not as common. So our ones here. So that means that the rotational speed or we call it the W, the angular velocity, divided by, or of the driver is going to be divided by the angular velocity of the driven. So as we look here, our larger number is always going to go on top. Now the next ones are going to be based on the radius and the pitch diameter. And the pitch diameter is going to be the one that we're going to know most often and most directly. You'll notice that the 2 goes on top here because that's going to be the larger of the 2 because physically our driver will be larger than our driven. Okay. And it just keeps it as, you know, a number that's greater than 1. Now, just as we had before, as we look at this and then we look at the velocity ratio, we want to know how many times does this driver have to go around before we get this to go around just once. So the bigger the differences between these two, the larger that ratio is going to be. Okay. All right. How come we don't have number of teeth here? We had ends for gears. Unless you have a timing belt, but there are no teeth on a V belt, right? Yep, it's smooth. It's just based on the diameters. Right. Good. Okay. All right. So there is that. Let's look at an example. Of course. All right. Oh, one last one. Did I forget that one on here? No, I didn't. I just didn't see it. Belt speed, okay? We want to know what the velocity is of how fast that belt is going. So VB, remember VT, pitch line speed for gears? This is the VB, which is going to be the pitch line speed of the belt, okay? And if we go back over here, the pitch line speed of the belt, how can I draw this? Pitch line speed, I'm going to go down here first. So as I'm rotating around here, I want to know how fast that belt is going. And so this, if I go at the top here, it is going to be the straight line velocity component of the angular velocity. Does that sound familiar? Of course it does. So this is our straight line velocity component of our belt. How fast is that belt going? And that's going to be in our classic distance over time, okay? So to calculate that, knowing a rotational speed and how far away from the center of rotation it is, look at what that equation looks like. Our velocity of our belt is going to be the radius, one, if you would, if I'm looking at the driver, it's going to be the radius of the driver times the angular speed of that driver in radians per second. Okay, not RPM. So this equation is very familiar to us. And now they just expanded out because most often we're working with pitch diameters. It would be the pitch diameter divided by 2 times the angular velocity of that pulley that we're on. And then over here, if you're working on the driver side, it's going to be the number 1s. If you're working on the driven side, it's going to be the number 2s. Okay. So that looks very familiar to us. So let's look at problem 11.1. So this one we're going to work together. I know that it's worked out here, but we'll work through it and then we'll compare our answers back. So here it says we have a belt drive. It's used to transmit power from an electric motor to a compressor for a refrigerated truck. The compressor must still operate when the truck is parked and the engine is not running. So we have a 10 horsepower electric motor rated at 3550 RPMs, and the motor sheave diameter is 5 inches. The compressor sheave is 7.5 inches. So this right here, the motor, this is going to be our input. Okay, so this is going to be, if you would, D1. All right. And then they're giving us the compressor sheave, which is the output. This is going to be our D2. Make sense? All right. So the larger one is D2, the smaller one is D1. And then we have here the motor itself is rated at 3550. That's going to be our W1. Okay. And then the horsepower they're giving us. Now, did they say determine an appropriate industrial size belt, the operating speed of the compressor, and the belt speed? Okay. All right. So what we're going to do is you'll notice that we want to know what is the operating speed of the compressor. So the compressor sheave is the 7.5 inch diameter, and the motor sheave is the 5 inch diameter. So if we know that the motor is going at 3550, we want to find out what is the W2 based on the ratio of the 2 diameters here. So as we look here, I'm going to kind of zoom out a little bit. This is example 11.1. So we know that D1 is equal to 5 inches. D2 is equal to 7.5 inches. We know that W1 is 3550 RPM. We need to find W2, right? We need to find W2. That's our first. And then we also need to find the pitch line speed of our belt. Okay. Those are the 2 things that we need to find. So probably wouldn't hurt to put our equations in a nice, place so that we can just reference them. So that was a great idea, BJ. So I'm going to turn my page here and we're going to write down some of the equations that we think are going to come in handy. Okay. So if I want to figure out what the rotational speed is of number 2, knowing my pitch diameters, which equation is going to help me with that? Shout it out. And these were the equations on just the last couple pages here, like 303 or 304 to 305 to 306. What are we thinking? Yes, our velocity ratio. Yeah, we want to write that on our equation sheet for sure. So we're going to put, so this is just equation sheet right now. We're going to kind of organize our thoughts. It's going to be our V belts. Okay. So our velocity ratio is going to be equal to our W1 divided by our W2 equal to our D2 divided by D1. Remember, the larger will always go on top. So when we get into physical size, we have to put the 2 on the top because the driven sprocket is going to be, or the driven sheave or pulley is going to be larger than the driver. And then we can do the radius as well. Okay, and that's going to be 2/1. Okay. Now, to get our number 2 here, because we have to find out what W2 is, we know W1 and we know both of our diameters, right? So for the first part of this problem, step number 1, we can calculate what W2 is going to be. So instead of writing out VR is equal to, we're going to just use this part right here. The W1 over W2 is going to be equal to D2 over D1, and then solve for W2 and then input our values. So go ahead and do that now. So don't forget to write out your equation in variable form, and we're just going to use these 2 parts of this. So D2 over D1. Okay. And we know 3 of the 4 variables. So I'm going to first rearrange. I'm going to multiply my W2 up and then get it on one side of the equation. So I'm going to have W1 is equal to D2 times W2 divided by D1. So that's going to go up. This is going to come down. So I'll do one more. W2 is going to be equal to W1 times D1 divided by D2. Okay. So this will be the rearranged version that I'm going to do. Now, you don't have to show each and every one of the steps on how to do that. I totally get that, but just in case, it's not a bad idea to write it out because we are doing a couple steps, and even I still do it just to be sure that I don't unintentionally put something on the top and it was supposed to be in the bottom. So now once I have my equation in variable form, I'm going to put my values or my numbers in. So I'm going to do 3550 RPMs. Now I don't need to change this to radians per second here, only when I have my pitch line velocity of my belt, which we're going to be adding in just a little bit. Oh, thank you. Talking and writing isn't as easy as it looks. It's really not. Okay. B1 is 5 inches divided by 7.5 inches. So my W2 oopsie. So make sure you're putting your units in all phases of the problem. You'll notice that the inches cancel out top to bottom, and we're left with RPMs, which is what we're interested in for the, angular velocity of W2 or of the pulley number 2. And you should get 2367, 2366.7, and the 6 is repeating. Okay. Any questions on that one? You guys do okay? And if you compare to the book, that's the number that they get as well. Okay. Like it. All right. So now the second part of this problem is going to be, we want to know what the belt speed is. Okay. The belt speed is that VB, or the pitch line speed of the belt. How fast is it going? What is that straight line velocity component of? So now that equation is actually at the top of this very same page. And I'm going to zoom in here so that we can see it. It's in that familiar form of velocity is equal to, this we've been using actually since velocities, right? That's like chapter 6. So we're going to take our radius of our pulley, or half the diameter, times the angular velocity of that pulley. But remember, this needs to be in radians per second, right? Radians per second. So let's add that to our equation list. Okay, so this is going to be whenever they ask for belt speed, okay, that's our VB, or they're using lowercase b. I'll use that so it's consistent. It's going to be equal to the radius of that pulley times the angular velocity of that pulley. So if I'm on 1, these have to be both 1s. If I'm on 2, they both have to be 2s. Okay. All right. So as we look back at the information that we're given, okay, the pulley that we know the most about, right, is pulley number 1. We did calculate the velocity, the angular velocity for pulley number 2, but we want to use the least calculated numbers, right? So if we can go back to using some of the original information, we want to do that, and we can, right? Even though we don't have the radius, we can get it with this diameter. And then if we have since we have our W1 and RPM, we just have to convert it to radians per second. Okay. So step number 2 here is going to be, we're going to use pitch line speed is equal to R1 times W1. So over here, I'm going to convert my W1 from 3550 revolutions per minute to radians per second. Okay. And we're like so good at this point, right? It's like you probably don't even have to like think about it anymore. Your hand just does it. You get 371. Yeah, okay. Otherwise, I'll do mine twice, but okay. And that's going to be the number that we're going to put up here. And then our radius is going to be our diameter divided by 2. So it'll be 2.5. Mhm. Mhm. Did you get the same number? 0.5, 0.7. Oopsie. Oh, that's fine. Yeah. Yeah. I like, well, you know what? And actually belt speed most often is in feet per minute. That's actually more common than any other units. So, I think I did mine 2.5 times 371.7.25 inches per second. Okay. So they kept it in, and then they changed it to feet per minute. Yeah, that is the most common. So why don't we do that? Let's put it in the units it's supposed to be. So we'll do one more inches per second, and then we want 12 inches, 1 foot. So those will cancel. And then we have 60 seconds in 1 minute. So just to be sure. Yeah. 46. I get 0.25, and that's going to be feet per minute is equal to our belt speed. And that is very typical to put it in feet per minute. That's the most popular. Okay. All right. Any questions? Nothing new here, right? Did you notice that? It's a total reapplication of the stuff that we learned in gears. That's what's kind of fun about it. You don't even need me anymore. Do this all yourself. Okay. All right, let's go back to our PowerPoint. Any questions? Everybody good? Or should I wait for a second? Are you just kind of checking things?
Yeah, no, I've got. That's all good.
You got it? Okay. Okay. All right. So we went through our example. Great. Let's do another example. Okay. So at the bottom of that very same page is going to be example 11-2. We want to determine the appropriate belt size and find suitable sheave diameters of stock pulleys that are listed in that table 11-1. Also select a belt length from 11-2 and calculate the corresponding center distance. Okay, so this is kind of like the full blown problem, and this is going to mimic, problems that you're going to be assigned in the homework. So this one's a little bit longer. So let's look at the problem statement again, which starts at the bottom of page 306. Okay, so we've got some things to do here. So it says here a belt drive is required to reduce the speed of an electric motor to a grinding wheel. Okay, and actually what's nice is they do have the picture of this at the top of page 307. So the motor is down here at the bottom and the grinding wheel is up here on the top. And notice that they are connected by this V-belt drive. Okay, so coming off of the motor is going to be our driver. Okay, our driver pulley, and then going up to the grinding wheel that's going to be going at that same RPM is going to be the driven pulley. In the problem statement, they're telling us that it's a 50 horsepower electric motor and it's rated at 1725 RPMs. So that means coming out of the motor, 1725 RPMs. So our W1 is that same number, 1725 RPMs. Okay. The grinding wheel, they want to be going at approximately 600 RPMs. That's what's desired. So that's going to be our W2. Okay, our W2. They want us then to take that information and do what we said in that problem statement. We want to find the belt size. So that's going to be a 3V, a 5V, or an 8V. Okay. And we want to find then suitable sheave diameters from that stock commercial list. All right. And then we're going to select the right, a belt length. Okay. And then we're going to calculate the corresponding actual center distance once we know when we're using. Okay. All right. So this one's got some steps to it. So the first thing that we're going to do is we need to determine what is our belt size. All right. And that's the step that they take down here. So they do have the steps here, but we're going to, again, write them as we go along because I think it helps to kind of clarify what's going on in each step. Okay. So determine. So we've got a 50 horsepower motor driving at 1725 RPMs. All right. So to determine what that belt is going to be, what the appropriate size for this application is, we're going to go to the top of page 304 and use this chart. Now I am going to give a disclaimer here because we're in kinematics and they're not really adding in one additional thing. You'll notice that this says design horsepower. Okay. When we get to machine elements, the design horsepower is really affected by your input and your output. And there's going to be a factor in between there that we multiply the original horsepower by. So for instance, if this is an electric motor, there's going to be a factor associated with that. And then also for the output, the grinding wheel, there'll be a factor associated with that. So our design horsepower is usually never the horsepower coming off the motor. It's going to be like ticked up a little bit, okay, because of either the volatility or the smoothness of the applications coming in and out of it. All right. So when we're in design problems, we will be actually calculating a design horsepower here based on some more information and then some additional charts and things that we can look at. So we're going to use just the horsepower here. And maybe I'm telling you that and you're like, well, it's no big deal, but design horsepower is more than just regular horsepower. All right. So we're going to take, did it say 10? It is. It is. And they're just not taking that into consideration here. So I want you to know that when we see design, there's usually something to it. Okay. It's not just strictly the textbook off the motor horsepower, but that's what we're using here. And that's okay. So 50 horsepower and 1725 RPM. So we're going to find where 50 is. Okay. And we're going to find where 1750 is. So 1750 and 50, right? So we're right about here. Now, you might say, well, that's kind of at the top, you know, of the 5V, okay? But even though it's at the top here, it's also closer to the 3V, all right? So we're not at the end of the application. If we would be on this side, closer to the 8V, I would cross over to the 8V right away, okay? You don't necessarily want to be the highest amount on the end of the capabilities of a belt, right? You actually want to be, if anything, on the beginning capabilities of a belt, all right, so that they last longer. And here where we're looking, we're close to the 3V, which would actually get smaller, so we're actually in a really nice place with our 5V belt. Okay, so 5V would be a good place to start. All right, now again, remember, design horsepower is probably going to push this in this direction. Even if this goes a little bit in this direction, we're still nicely in the 5V area. So I think it's a good application, and it's a good value to stick with. So that's what they decided on, was a 5V belt. Okay. So for this problem, we're going to want to identify that that's going to be our belt. So starting off here, that's one of the requirements that it asked us for, to choose a belt. So this is example 11.2. And step number 1 is 5V belt. Okay. We can just, whatever. That's one of our answers. Now what we need to do is we need to determine what is the diameters of the shivs that we're going to pick, okay? And the requirements that we have here are, these are going to go from 1725 RPMs to 600, okay? So we've got to pick a standard pulley for each one of those that are going to help us obtain that difference between 1725 and 600, okay? So the belt, the shivs that we get to choose from are going to be on page 303 on this table right here. Okay. And we're going to be looking at this middle column, okay, to be the diameters that we can use. Now, where to start? We're going to recall that our velocity ratio is going to be equal to our W1 divided by W2, and we can set that equal to D2 over D1. Okay. Now, I'm going to rearrange this to solve for D2. So I'm going to take my D1, I'm going to multiply it up here. So I'm going to say D1, okay, times W1 divided by W2 is going to be equal to D2. Now, our known values here, we know that W1 is 1725, and we know that the desired W2 is 600. Okay, and we're going to try to get as close to that as possible. So if we plug those two values in and we say D1, and if we say 1725 divided by 600, that's going to be times 2.875. Do you see that? The RPMs cancel top to bottom. So this is our velocity ratio. We're taking the velocity ratio, multiplying it by the whatever our D1 is, and we're going to get D2. Okay. So now we go to our chart and we find out what are our available D1s. Now remember, D1 is the smaller of the two. Okay. So as we look here, I mean, the ones we have to choose from are this list right here. So I'm going to start with, I never want to start with the smallest one. I don't know why. I just don't like to. So I like to go a couple in. I'm going to start with 9.4. Okay, 9.4. And I'm going to multiply it by our factor and see if there's anything close to create that same ratio. Okay, so I'm going to take, now this is just trial and error. That's all this is. So I'm going to take 4.9 inches times 2.875, our velocity ratio. It's going to be equal to, so this, we're trying out this as our D1. Okay, so 4.9 times 2.875. And we're going to get 14, okay? 14, and that would be inches, right? And so this would be a possible D2. You got what?
13.9.
Oh, there is a 13.9. Yep. So if we look here, there we go. There's a 13.9. So then we can see, okay, if I do a 4.9 as my D1, how can I do this? Oh yeah, up here. So if I know my D1 is 4.9 inches, right? And if I pick my 13.9 as my D2, I can set this equal to my W1 is 1725 RPMs, right? And I solve for my W2. Shoot, it's on the bottom. So I'm going to put my W2 up here. I'm going to put the 13.9 down there, and I'm going to multiply the 4.9 up there, right? Do you guys see that? So my W2 is going to be equal to 1725 RPM times 4.9 inches. Oops, sorry, 4.9 inches divided by 13.9 inches. Those inches cancel. So what does my W2 come out to be? How close am I to 600? Ooh, not bad. Okay, so this pair would provide for us a velocity ratio, and we would get 608 as our number. That's not bad. So we're gonna put this down here. We're gonna say, okay, D1 can be equal to 4.9, D2 can be equal to 13.9. Hold on, we're not done yet. We're not done yet. And our W2 then is going to be 608. You're just like ready to pack it up. Like, we're done. That's close enough. Let's see if we can get closer. So this would be the process you would go through. You would try again, and you would try to get as close as possible. So we're gonna, and it's easy enough to do. You can go maybe to the next number, and you can say, all right, what if I do 5.1? If I do 5.1, see, and you don't have to write all of these out, all right? But I would do 5.1, and I would take it times 875? Yeah. I'm getting 14.6. Ooh, nothing. Let's try. Adam's done. He's like, I think it's good. Let's try 5.4. Am I the only one like wanting to get closer? Ooh, 15.5. 15.5. Try this one. Let's see this. Let's see how this one works out. So we're gonna try 5.4 and 15.5. See what we get. I think we might be pretty good. So here we would have, I'm gonna rearrange my W2 is going to be equal to W1 times D1 divided by D2. There we go. 1725 RPM. Sorry, I'm at an angle here, guys. Our D1 is going to be 5.4 inches, and our D2 is going to be 15.5 inches. That cancels. So our W2, did you get it?
600.
Oh, 600 point. Now, don't you feel better? Like, I mean, seriously, 608, 60, not even 601. Oh my gosh. You did, yeah. We'll go with this one. This is even better. This one's even better. So the pair, now this would not be non-valid. I mean, it would be fine, right? And it is close enough. And you as a designer get to make that decision, and you would know more about your application, how critical it is. But we can be right on practically. We want to do that. So we're going to go with D1 is equal to 5.4 inches. Our D2 is 15.5 inches. And our W2 then is going to be our 600.96 RPMs. So this is going to be the one that we're going to proceed with. Okay. Everybody feel good about that? It's a democracy. If it's cheaper than the other one. Yes. There you go. We're going to have to look at costs now. Yep. And those are, you know what? Jesse, that you're actually really correct in thinking about those things. It's one thing if we can get this to work and be like right on, but if this drive, let's say we use the same size pulley, you know, one of these pulleys in another area or the same pulleys in another area, and it's going to reduce the number of service parts that we're going to have to provide, that's a great reason. 608 then is close enough, right? So, so there are other factors in before making that final decision. Okay. All right. So we're going to proceed here. These are going to be the numbers that we're going to use. So let's see. So we picked our, so far, what did our problem ask us to do? We wanted to pick our size of our belt. We wanted to pick our pulleys. We've got our pulleys picked out. Okay. Now we need to select a suitable belt length, So now that we have our pitch diameters figured out, we're going to go back to page 304, and we're going to add some of these things to our equation list. Okay, our equation list. So I'm going to go back to our equations for belt drives. This first one here is where we're going to be picking our center distance or making sure that it's within this range. Okay, so this range is, so this is going to be our range of our center line or center distance, range of center distance. Okay, and we want that to be between the diameter of D2 has to be greater than our center distance is going to be in the middle of that. And then it has to be less than 3 times D1 plus D2. Okay. So we'll figure that out in just a second. We're going to write the rest of these here so that we have them handy. Then as we go down a little bit further, the next one is going to be the length of our belt. Okay. The length of our belt. So once we I'm going to say it, we're going to pull it out of the air. Like we want our center distance to be about. So based on the range right here, we're going to pick a number in the middle because our problem doesn't give us a center distance. Okay. It's like, pick what you want, which isn't necessarily practical. I'm going to keep saying that. Kind of drives me crazy. Like give me a center distance, but we can pick it as long as it's within that range. We're going to pick a center distance and we're going to put it into the length of the belt equation next. And then we're going to find a length of the belt. And then we have to pick one off of our list. That's going to be an actual one and then go back and recalculate what that actual center distance will be. So the next thing here we're going to write down is going to be the length, capital L, it's going to be 2 times C plus pi over 2 times D2 plus D1 plus D2 minus D1, square that and divide by 4C. Okay. So that's that same equation. Now this is to determine, you know, based on the center distance that we pick within that range, what's the closest belt that's made continuously that we could choose? Do you see that, Jesse? The first one is a plus. The second one is a minus. Mm-hmm. Is it real? No, I didn't. See, we're better. We're better. Yeah, 608 was great. Is it really? Again, they're the designer. We're better. Yeah, no, that's fine. Now, once we do our initial length, then what we're going to do is we're going to go over here and we're going to find an actual length based on that. Okay. And then once we find our actual length, we're going to come back and then we need to know what our actual center distance is because it's going to change based on the belt that we actually get. Okay. So good. Now, what? Okay. So now this B is really nothing. It's only to make the equation shorter. That's it. So we're going to calculate B first. So B is not like an actual variable. It's just to make this smaller because otherwise you would have to put this in for this B and this in for that B. What was that? I know. So I'm just going to put B. Okay. And it's, again, it's kind of a nothing variable. It's just a step in the equation. B is going to be equal to 4 times L minus 2 pi times D2 plus D1. Okay. And then once we have B calculated, then we're going to plug it into the actual C, which is the center distance, b plus the square root of b squared minus 32 times d2 minus d1 squared, all under the radical. And then divide all of that on the top by 16. And those are really all the equations that we need then. Okay. So I guess there's more than 4. I thought there was like 4. Oh no, there's 2 more equations. It's the wrap, but those aren't a big deal. I don't even know if they ask for them in there, but it's a good thing to check at the end. The last 2 equations here, we might as well put them on our sheet, are the wrap equations. Okay. It's determining how much wrap we get on our first pulley, which is going to be our theta 1, corresponds to the angle of wrap on our driver, and theta 2 corresponds to the wrap on our driven. Okay, so not a bad idea to put those down as well. Yeah. All right, we can go back to our problem now. And we are going to calculate our corresponding belt length and the center distance. So we first need to identify the range for which our center distance has to be between. Okay, so I'm gonna turn my page here. And this is going to be, I think I'm on step number 3. Yeah, step number 3. Okay, we need to figure out what D2, C, and then 3 times D2 plus D1 or D1 plus T2, right? So this number right here, D2, based on the shiv that we picked, our D2 is 15.5. Okay, and our center distance has to be between that, and then 3 times 15.5 inches plus 5.4. Okay, so 15.5 plus 5.4 times 3. So we need to be between 15.5 inches and 62.7 inches. So it's a pretty big range. All right. So now let's just kind of see what they picked. They picked what? Oh, they had, yeah, they had different gears. They had, or different pulleys. That's okay. Well, we'll pick our number. Ours is better. It's closer. I'm going to ask those who are on the chat. Maybe they're sleeping. They're not sleeping. What do we want our center distance to be? Those who are in virtual land, pick our center distance. We want it to be between 15.5 and 62.7. Anyone, pick a number. Maybe I should. Hello. So those who are, this is your chance online. For those who are virtual, you get to pick our center distance between 15.5 and 62.7. Anyone, write in the chat box or yell it out if you've got your microphone on.
Someone not there. They all walk away from their computers.
We caught that.
Sorry, I was muted.
Oh, here we go.
Hey,
So I was trying to say, the center distance, we're just choosing an arbitrary center distance or
Exactly. This problem unfortunately doesn't give us a number. And in real life, you would have like a range that you would know that your center distance is going to be in. So we get to pick between here and here. So what's our number? Is that Logan?
yeah, I was gonna
Yeah.
say like 20 inches.
20 inches. That sounds good. All right, we're going with 20 inches. We want our center distance to be 20 inches. All right. Perfect. So now what we're going to do with that, oops, David's back. Okay. So, oh, are you in the chat? No, it's a different David. Are you Brian?
Yeah.
Oh, shoots. Dang it. Why do you know why? David and you kind of look the same. Now, again, if you'd be sitting next to each other, he has dark hair and he sits here. So I always get you guys mixed up. David has been online. I'm sorry, David. Laptop died. That's okay, David. I thought you were in the room with me anyway. So it's totally fine. Totally fine. Yeah. So, I'm sorry, Brian. That's okay. I'm sorry. Okay, we're picking our center distance as 20. So that means we need to, I'm gonna grab my my equation sheet out rather than flipping. Okay. So now what we're gonna do is we're gonna determine a length of a belt based on this center distance. Okay. And this is gonna give us kind of an estimate of the belt that we're going to pick. Okay, so go ahead and use the center distance, your D1s and your D2s in this equation, okay, and calculate what your trial length of our belt would be based on a 20-inch center distance. Okay, so this is going to be L, and I'm going to call this trial because this isn't going to end up being our actual length. Okay, it's just going to be based on we're wanting this to be around 20. So we're going to be 2 times C plus pi 2 D2 plus D1 plus D2 minus D1 squared on top divided by 4C. D2 is 15.5. You know, another point too, when we pick elements for a drive, most often you want it to be as compact as possible. So I'm not saying that their design isn't good, but usually you kind of go towards I want a more compact design rather than a big thing.
For this grinder, it's stand up, so they want to put the motor as close to the ground as possible, keep the weight. So maybe they're trying to get a height.
You might be right. You might be right. Yeah. Yeah. T1 is 5.4 inches plus 15.5 inches. Square that divided by 4 times 20 inches. It's kind of long. Just I don't know if anybody got this far yet, but I got 74.11. Did anybody else?
really close to that.
Okay. Okay.
24.1.
74.1. Okay. 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 All right, good. So now, as we look at this number, this is based on what we're thinking about a 20-inch center line, but we now need to pick a belt that is close to that length, because it's going to be a continuous belt that we're going to get at Napa or somewhere like that. So we're going to go to the 5V belts and we're going to look, what is the closest to 74.11? We've got a 75, right? So now if we pick the 75, it's going to change our actual center distance a little bit. And that's what we now want to calculate. So we're going with a belt length of 75. So we're going to say our L actual is going to be equal to 75 inches. Okay, so that's one of our answers, because it wants to know what is the length of the belt that we're going to choose. So then our last part of our problem here is going to be calculating the actual center distance. Okay, now the actual center distance, as I said before, starts with B. Okay, we have to calculate B. We're going to get a number for B, and then we're going to put it in each of these locations in the center distance equation. Okay. It's a nothing. All it is, it's to make this less complicated.
I see.
Yeah, that's all that it is. So it's really, it's kind of like an intermittent calculation. No, it's not a belt. Yeah, it's just an intermittent calculation. Yeah. Just as if anybody has their B at 236.54.
Yep.
Yep, okay, great. So 236.54. And now we've got to put it into the big one. Yep. So good. All right. Oh, no, it's not yet. I got 29.125. 129. Oh, well, rounding, right? How about those who are virtual? Did you guys get the same number? You
Yeah,
got 0.13.
Yeah, they're pretty much right.
that's what I got as well, 0.13.
You got that too? Okay, awesome. So Logan, since you picked a center distance of 20, are you happy with 29? Please be happy.
Yeah.
Okay.
Yeah.
And there's another decision. There's another decision that you make, you know, like when you're looking at this and you get that actual center distance, now you're going to evaluate and you're going to say, am I okay? David got 29.52. I'm calling that good, David. Awesome. Okay. Yeah. So they didn't give us really any guidance here. So Logan is going to say, yep, I'm happy with that. All right. So I think we delivered everything they wanted, right? If we look back at the problem, and I don't know if we did it in the exact same way that the book did, which is fine. They wanted, as we look at the problem statement, they wanted the appropriate belt size. We did 5 Vs. They wanted suitable sheave diameters, which we pulled off of the chart, the 15.5 and the 5.4. Pitch diameters, suitable belt length, which we picked, was it 75, right? And then we calculated the corresponding center distance. There you go. There's the problem. So this mimics, I think, at least 1, maybe 2 problems that you're going to do for your homework. Okay. So why don't we take a quick peek at the homework that's going to apply to the belt portion here. Okay. So, are there any questions I should ask online? Are you guys okay with what we got here and feel confident? Crickets. That's okay.
Yeah.
You're good, Logan? Awesome. Thank you. So I'm going to take a peek at assignment number 6. Assignment number 6. And let's see, these two. I'm going to look at the back of the book. I forget which numbers correspond here to the belt stuff. So all of these problems are at the end of the chapter. So I've got 2, 6, 8. Okay. So I'm going to go underneath here and I'm going to move our chat box. So 11.2. This is a belt problem. So we've got a motor operating clockwise at 1150 RPM. It's coupled with a belt drive that rotates an industrial exhaust fan. The diameter of the motor sheave is 5. The sheave on the fan is 12. Determine the speed of the driven sheave and the belt speed. So this is like a W2, right? The speed of the driven sheave, that's a W2, and the belt speed is going to be the VB. Okay. So that's like the first example problem that we did. Number 6, I think, is a very similar problem. Rotates at diameter, determine the required speed. That's going to be a W2 again. And then the belt speed is going to be a VB again. Okay, so same problem, different numbers. Number 11.8. 2 sheaves have a diameter of 5 and 12. Determine the center distance of a drive utilizing a 72-inch belt and compare the center distance to the ideal range. Oh, okay. So here's a little bit different problem. Also determine the angle of contact. So what you're gonna do here is you're gonna determine the center distance size here based on what they have going on. 72-inch belt is the actual length. And then you're going to determine what the actual center distance is and then the angle of contact on each one of those shibs. That looks fun. You guys are lucky you get to do that problem. Number 11-8. That looks
Oh,
fun.
that's the one with the wrap, isn't it?
Yes, yeah, it's gonna be so good. And then the next one that we have, belt drive selection, this is gonna be like the very last example problem that we did, where you're going to select an appropriate belt size, commercially available shivs, and a belt for this application, and also calculate the actual belt speed, VB, and the center distance. Okay, so that's like that last example problem that we did. Yeah, and then those are the problems for the belts. So since we're at 6:30, I think this is a good time to just take a break in the middle of our lecture, because we'll come back and we'll finish up and then we'll look at chain drives. Okay, so I'm gonna stop the recording here and then we'll come back. I'm